Okay, so for part 2 of 6-1 notes here, we're picking up with example 2. We just did the beautiful derivation of where centripetal acceleration came from, right? So that's where we left off on the previous part. And again, guys, that derivation comes from using some calculus, and I know that calculus can be pretty tough to follow maybe as I work through it. So if you do have questions on where that came from, again, and at the very end of part 1, let me know. Let me help you out with that if I can. But anyway, let's continue on with example 2, and then we'll try and pick up several more examples in this section of the notes. So anyway, example 2. The radius of the Earth's orbit around the Sun is 1.496 times 10 to the 11th meters. We are going to go ahead and assume that that is from the center of the Earth to the center of the Sun. So we'll assume that that includes the total distance there between the objects. A, what is the centripetal acceleration of the Earth as it moves in orbit around the Sun? Well, good thing we just derived that equation, right? Centripetal acceleration of the Earth would be v squared over r. So we need to figure out what the Earth's velocity is as it orbits around the Sun, right? Because they give us the radius, they give us that distance, so that's no big deal. We just have to find our velocity and then use that to help me find the centripetal acceleration. So how do we find the velocity? Well, the velocity, right, it's either one of two things. It's either v equals r times omega. My linear velocity equals the radius times the angular velocity, which actually may help us with part B. If you kind of look ahead, they ask us for the angular speed, so that actually might help us with part B. The other way that we can find velocity for a situation like this is, again, we're going to go ahead and assume that the Earth's radius, or that the Earth's orbit, is a relatively circular orbit. And because of that, we know that the velocity would equal 2 pi r, the circumference of that circle, divided by the period of the orbit. Well, we know 2 pi, right? Those are both constants, and we know the radius, and then we secretly know the period, right, of the Earth's orbit, and that becomes the key to this question. We know that the period for the Earth's orbit is 365 or 365.25, if you want to be a little bit more accurate. 365, excuse me, not 2. But anyway, that's how many days, right, the orbital period of the Earth is as it rotates around the Sun. So we actually know the period, we know the radius, we can find the Earth's velocity without too much trouble. So my velocity, again, 2 pi times the radius of the Earth's motion, so 1.496, times 10 to the 11th, which again we're assuming is from the center of the Earth to the center of the Sun. And then the total period, which I'm going to go ahead and just show kind of the conversion down here. So I am going to use 365.25 days to be a little bit more accurate, 24 hours per day, and then 60 minutes per hour and 60 seconds per minute. So make sure you're just careful in this calculation, and I end up getting about 29,786 meters per second. So about 29,800 if you choose to round that off a little bit, but that ends up being then the velocity for the Earth as it orbits around the Sun. So then they asked us to find the centripetal acceleration. Well, no big deal. I now know the velocity is 29,786 meters per second. I'm going to square that and then divide it by the radius, which again is that relatively large 1.496 times 10 to the 11th meters right around the Sun. So anyway, I calculate that measurement and get a pretty small number here. So 0.0059, 0.006 if you prefer, but I'll go ahead and take it a couple decimal places there. But 0.0059 meters per second squared. So the centripetal acceleration that the Earth experiences is not a particularly high one, right? Which we might expect, though, because the Earth is following a very big orbital path, and it takes a while for it to complete one cycle. So not necessarily an unreasonable measurement, but obviously it is very low for us. But anyway, part B asks us again to find the angular velocity. So again, if I want to find the angular speed, the angular velocity, a couple different ways I could go about doing that. One of the easiest ways might just be taking advantage of the fact that, again, we know the relationship between linear and angular measurements. My linear velocity, which I just found up above, equals the radius times my angular velocity. So if I'm looking for that measurement, I can just use my linear velocity again of 29,000. Let's scroll up so I can actually see it. 29,786, and then the radius of the Earth's path, which obviously is a very big number there, times the angular velocity r omega, and then solving for r omega. And I end up getting 1.99 times 10 to the negative 7th radians per second. So anyway, hopefully part B, once we've established part A, is not too terribly difficult. But a good question to review, one to go back and again, part A, making sure we keep it simple. You don't have to remember the equation for orbital velocity to get to part A. We will review that as the chapter continues, but you don't need it for this particular. Okay, so example 3 here, I'm going to try to go through this one pretty quick because my bet is you guys are probably okay with it. But the graph down here is giving me the angular position versus time. They want me to describe the wheel's motion and then draw an angular velocity versus time graph. So briefly describing this, I won't write it down, but feel free to write it down or make notes as I do. Right, but if I look at the first 3 seconds here, right, so what's the graph doing for the first 3 seconds? Well, we're looking at position versus time, so what does the slope tell me? Well, the slope tells me the angular velocity, right? If it's position versus time, the slope is telling me the angular velocity. And that's true for really all 3 phases, if you will, of this graph. So again, for the first 3 seconds, what is it doing? Well, the object, the wheel or whatever's spinning here, right, is traveling, it's moving with a constant angular velocity of, if we look at the slope, it'd be 6 pi divided by 3, so of 2 pi, right, in the positive direction. So for the first 3 seconds, the wheel is moving with an angular velocity of 2 pi in the positive direction. For the next 2 seconds, from 3 to 5 seconds, it's now moving with an angular velocity of negative pi, right, in the negative direction, obviously. And then finally, for the final second there, it's moving with an angular velocity of 0. So it's at rest. So again, describing the wheel, make sure you're pretty comfortable translating to and from these graphs. When I look at making my velocity, my angular velocity versus time, so my omega versus time, I know again for the first 3 seconds, so 1, 2, 3 seconds, the wheel here is going to be spinning at a constant angular velocity of 2 pi. Right? So for the first 3 seconds, my angular velocity is constant up here. Then for the next 2 seconds, it's a negative angular velocity, right, because it is going back in the other direction. So then down here at negative pi, I'm moving with a constant velocity of negative pi for 2 seconds. And then finally for that 5th seconds, from 5 to 6 seconds I should say, so I guess the 6th second, I've got 0 angular velocity because the slope is 0, and so I'm moving on the x-axis for my angular velocity versus time graph. So anyway, much like what we did early in the year when we did our velocity versus time graphs, our position versus time graphs, you still need to be very comfortable doing the same for angular motion as well. Example 4 here is probably a pretty easy one, so feel free to pause if you guys want and do this on your own first, but I'll work through it. Like I said, I don't think this will give you any trouble, but I'll work through it should you need it. So what is the ball's angular velocity? Really the only thing I will emphasize with that is our standard units for angular velocity should be in radians per second. Again, that just makes working with kinematics a lot easier, so that should be our standard unit. Other than that though, this one hopefully isn't too bad. My angular velocity again is defined by my change in angular displacement, my change in theta over time. And again, I'm gonna try to put that in standard units. So it says it makes 2 revolutions. Well, 2 revolutions, but each revolution is how many radians? 2 pi radians, right? So it'd be 2 times 2 pi. And then the time obviously is just given at 1.20 seconds. So I calculate this, I round this off a little bit. You can keep it in terms of pi. I think I went ahead and rounded it off. It ends up being about 10.5 radians per second. So my angular velocity, not terribly difficult to find. So then part B is kind of just a quick extension of this one. What is the ball's angular position at 2 seconds? And really again, the big reason I threw that in, we need to get very comfortable with the fact that when they ask us for the angular position, they're really looking for theta, right? They're looking for what's our theta. Well, if we're assuming that this is still a constant velocity, right, if it's moving at a constant velocity, again, we know delta theta over t equals that constant velocity. And since I just figured out my constant velocity is 10.5, I'm looking for what's the angular displacement, what's my change in displacement after 2 seconds. So really then just solving for this, delta theta would be equal to 10.5 times 2, so 21 radians would be my angular displacement. It does say assume we're starting at 0, so we'd start at 0, we'd add 21 radians to that and end up at 21 radians. But anyway, Hopefully, like I said, example 4 I think is pretty straightforward, pretty quick and easy. So then with this example, hopefully it's one not too bad. Again, gives us a graphical representation. Really the biggest thing you have to be comfortable with is the convention that clockwise is typically defined as the negative direction, right? It's defined as the negative direction. Because that otherwise you'd have two choices, you don't know which one to choose from. But anyway, particle moves clockwise around a circle at a constant speed for 2 seconds. So that tells me the slope is going to be constant for 2 seconds, right? So constant slope for 2 seconds. It then reverses directions, moves counterclockwise, so now a positive direction, at half the original speed until it's traveled through the same angle. So that second sentence tells us a whole bunch of information. It tells us it's now going in positive direction. It has half of the original speed, so half of the slope. So we know it should end up being less steep. And then it has traveled through the same angle. So it should end up back at the same position that it started with. Right? So through all of those pieces of information, and probably without even digging into it as much as I did right there, I think you guys would be able to pick out, hopefully, option B is the correct option, right? Initially, I move in the negative direction. After 2 seconds, I move back in the positive direction, so I'm moving back in the positive direction with half the speed, so the slope is less steep, but then I end at the exact same position that I started with. So anyway, option B is by far the best graph for us. Hopefully this would be something you guys could make on your own if need be. Okay, so bringing a few more concepts that I've already alluded to a few times now, but kind of bringing them formally out, right? So how does the linear or tangential velocity relate to the angular? Well, that's the equation I've referenced a few times already. The linear or tangential velocity is the velocity we're used to, right? It's our v, it's our change in x over time. How does it relate to the angular velocity? Just the same way that the linear position relates to the angular position. It's just the radius times the angular velocity. Right, so we saw in the very first couple slides that x equals r times theta. Notice that same pattern is true for linear velocity. How do we find the tangential acceleration? Well, acceleration is the only one you have to be careful with. Tangential acceleration is saying what's the acceleration tangent to the circle. And that pattern follows the exact same patterns we've seen twice now. Right? The tangential acceleration equals the radius times the angular acceleration, which is our alpha. So again, that relationship is still true. That does work for tangential acceleration. Here's where you have to be careful is the fact that we know, going back to the last couple slides, that we have to have a centripetal or a radial acceleration as well. Right? So we might have a tangential acceleration if the velocity is not constant. But I have to have a centripetal acceleration if I'm moving in a circle. So how do I find that in terms of the angular velocity? Well, centripetal acceleration we've already defined, we've already derived it, is v squared over r. What did we just say about the linear velocity? Isn't the linear velocity really just radius times the omega squared and then divided by r? So I end up with r squared omega squared over r, which obviously simplifies one of the r's out, and then I end up with the radius times omega squared. So I've got centripetal acceleration equals r omega squared. Now you never actually need this equation, because if you have r and omega, can't you find the linear velocity anyway? Right? So if I have r and omega, I could just find the linear velocity and then just plug that into the centripetal acceleration equation. There's nothing wrong with doing that. But if you want a shortcut, if you want one step shorter here, then you could certainly just plug it into this equation. So then the real question becomes, and again, this is probably the trickiest part. I hope most of us are okay with this, but definitely something you want to pay attention to as you go through the examples. How do we find the total linear acceleration? Or even if they just asked, what's the linear acceleration? Right? You have to realize when they ask for what's the linear acceleration, we have both the possibility for tangent and centripetal acceleration. So if I ask you to find the actual linear acceleration, the total linear acceleration, you have to find both of those and then do a Pythagorean theorem with it, right? And I'll show you why we have to do that here in just a second. But I have to find both of these and add these up as vectors, right? So again, going back to the circle, if at this point we have a tangent acceleration and a centripetal acceleration, then the total linear is going to be the resultant. It's going to be the sum of those two. Well, as vectors, if I add those two up, that means it's going to be, right, the hypotenuse of that right triangle. And that's where this equation comes from. So you definitely need to be comfortable with finding the total linear acceleration, right?